Okay, there we are. My apologies for this little technical difficulty. The experiment today is to learn about this terminal widget library. This is a program framework to make screens on a terminal with some element of interactivity. I have some experience working with this kind of widget framework in other programming languages, namely in C with the ncurses library and in Rust with an extremely well-designed cursive library. And today I would like to give a try to this library called tview for the Go language. I don't have too much preconceived notions. It has been recommended to me. It seems to have good reviews. And I want to try to make my go-to programs that I use to learn programming languages in that framework. So if I go to my terminal here, this is a program I wrote in Rust that does what I like to do usually, and that is a representation of the Mandelbrot set on the terminal with some element of interactivity with the keyboard. I'm going to start the keyboard display to show what I'm talking about. Here we go. So if I run this this program, I get a representation of the Mandelbrot set on my terminal with some kind of ASCII art. And the interactivity comes from the keyboard shortcuts. I can use the page down key for zooming in, page out to zoom out, the arrow keys to navigate. And then if I combine both together, I will get some element of viewing the intricate details of a fractal on my terminal. So the entertainment value is medium. It's fun to see that it's possible with a terminal to see mathematical shapes. This particular program is only displaying with shades of gray. So the beautiful colors that people know about this type of fractal are not available here. And it's somewhat slow. So this particular version is in Rust, and the slowness comes purely from the terminals. The computation itself in the program is rather fast. That means in particular that I can properly zoom out by making the font in my terminal much smaller. So excuse for the flickering. And you will see that as I decrease the size of the font in the terminal, I get more details in the picture. And the program is not particularly slower to compute. The slowness comes mostly, as I said, from the terminal display. So, and then I have some other keys. I seem to remember, what did my editor say about this? Oh, no, it's too small. Let's zoom back in. So I have an R key to reset the display to the default parameters. So I like this kind of program because it achieves three different things. One thing is that it demonstrates that the program has the programming language has some computation abilities. This particular figure requires to compute with complex numbers, and the ease of the computation is directly dependent on how much operations are available on complex numbers in the language itself. The second advantage of this program is that it demonstrates whether the program can support properly Unicode characters. Programming language, sorry. So these characters here are in the modern age are not anymore represented by some low value codes in the IBM code page, but instead as what are called box characters in the Unicode plane. So in order to make this picture look this way, I need to have output functions in the programming language that are able to process Unicode, at least via UTF-8 output to the terminal. And the third aspect is that it allows me to explore how to make an interactive program on that language or that framework. You see here, I have a program that replies to key inputs. If I was to use mouse input, would be similar. The idea is that there must be some kind of callback or event loop and an ability to register handlers for those events. If I look at the Rust version of this, the program is rather simple. I create this cursive output screen, a global callback key for quitting the program with a Q key press. Then I have my supporting data structure with the mathematical parameters of the figure. And I ask then the cursive library to draw a canvas with full screen, and such that every time the display is refreshed, for example, as a result of resizing or whatever, I will have this callback do_mandel call that is responsible for drawing the figure on the screen. And if there is a key press, there is another callback that is called move_mandel that processes the key press and changes the parameters of the figure before it gets resized. So the callback here will be recognizing the key presses of interest. You remember the arrow keys move the figure around, so that changes the center coordinates. And then the page up and page down, zoom in and out, that changes the ratio parameters. And then I have the R key to reset the parameters to default. And the drawing here is done by a computation function. Well, it's what it is. Its formula is rather simple, and then there is a drawing code here, which in this particular case uses the pseudo characters in Unicode here at the top of the screen, and draws them on the screen at the coordinates. So this is the Rust version. It's not super exciting. I wrote this maybe a year or two ago, and the goal today is to do something similar, but in Go. And using the TView framework. So the way I want to achieve this is by processing in multiple phases. So there will be a plan, and the plan is make a small, or if I want to say MVP version of the core computation. The one that shows the Mandelbrot set within with a set of given input parameters. Then I want to have a conversion of the computation output to the screen that is not yet interactive. And then we will integrate with the keyboard event handlers. All right, so the core computation essentially is a double nested loop. It does something for every pixel on the screen. So if I simplify this, I will say it's more or less something like this. I'm going to look at every coordinate on the X. Then I have every coordinate on the y-axis. And then I need to create a complex number for this. It's called C. I don't know how this works. Let's call it 64 or 128. Depends on the precision I want, I suppose. And then I'm going to start with a Z is 0 or C is the first iteration. I don't recall. Let's peek at the other one. It's C, okay? And then I'm going to iterate this, and there will be a maximum number of iterations. And I'm going to make it 100 for time being, doesn't really matter too much. I need to start. And the way it works is that we compute z is c times c plus c. That is the core of the computation. And you see here it's pretty nice that I have complex numbers in this language, because if I didn't, I would need to expand this formula into its principal component. And the next step is to verify whether we have escaped the whether the series diverges. And the diversion for creating the very well-known figure is decided by looking at the amplitude of z and comparing it to 2. So for this, I need this the magnitude. So the formula is really if the magnitude of z. So I don't actually know the name of the complex magnitude function in Go. We'll figure that out in a second. So if abs2 is greater than 2, then we have escaped. That is the rule. I actually don't know. So max x, max y. I actually don't know how the math complex number is called in Go, so we're going to figure that out. What does it have? So these are for just floating point numbers. Maybe there is a sub-package math complex. Let's see. No, it doesn't. Complex. Built in. That doesn't help. Okay, let's do math. Oh, CMPLX. There is a package called CMPLX. CMPLX. There we go. So I could use the ABS. ABS function, but I also remembered that the ABS function is going to do a square root, and I don't need that. I actually don't remember. How does the complex numbers work in Go? Can I extract, say, real and... Could you please make the font... Oh, absolutely. My apologies. I will make the font bigger. That is my fault. So Go long complex. So I can make numbers this way, and then I have real and image. Cool. Let's make the font a little bigger. There we go. This programming exercise does not need a small font size, so I suppose this will be adequate. So I could do cmplx.abs. That's the core formula, and that is we're going to start with this. But the real deal is later to accelerate. Really what we're going to do is that real of c times real of c plus imag of c times imag of c is greater or equal to 4, because the absolute, so the magnitude of the number is the square root of the sum of the squared coordinates. And so if the square root is greater than 2, that means the square is greater than 4. So we don't actually need to compute the square root, but it's okay. This is premature optimization. We don't need to do that right away. And then based on the remaining value of I at the end, we are going to make a drawing. And so we have some characters. And here I actually don't want to type them, so I'm going to copy paste them from the Rust program. There we go. And we are going to compute a value to print out. And how do we do this? We take the value of I, modulo the length of the boxes. That gives us a value between 0 and the size -1. And then we take one of the elements from that box and we print it. And at the end of every row, we are going to print a new line character. Expected expression and many errors. So where is the error? Boxes. It's go. This is the way to declare an array of strings. All right, max y. And if I do this, this is a test, and I'm just printing them directly. I'm not making this interactive. It's just because my number one step in my plan was to make a core computation. And so 100 in x and 100 in y, I'm going to switch this up because the row coordinates in the terminal output is switched over like with rotated from x to y. So it's complaining that there are things I haven't defined. Oh, of course. And then we're going to call this computation. I don't know. We have a lot of rows and columns in this terminal, but we don't have that many. So let's keep the... Okay, I don't know how many rows I have. Let's keep this smaller. So we're going to make 80 columns and 20 rows. And then call the compute program and then try that. Too many arguments to conversion to complex 64. I don't understand this. It's supposed to tell me that I'm supposed to be able to create a complex number from two different values. Oh, it's just complex. And the ABS argument wants me to have a okay. Let's make them bigger. I'm not picky. Yeah, better. This did not work. Everything is, well, seems to be white. So the reason why this happened is actually expected. We have iterated from 0 to the max value, but within the coordinate system of the terminal. But the interesting coordinate system for this figure is when x goes from -2 to +2 and y goes from -2 to +2. So we need to scale the terminal coordinates into the mathematical coordinates. So these ty and tx are going to be my terminal coordinates, and I'm going to scale them. And so for this, we are going to have x-min, x-max is 2, and y-min, y-max is going to be -2. And now I need to scale them. So let's scale first y, and the way to do this is to be y-min plus y-max minus y-min times, so that's the amplitude, and that's going to be max x divided by float 64 of max x. And that is the amplitude, and for this I'm going to be float 64 of ty times this. And now I have a scaled y, and now I can have a scaled x. It was max y here. X, 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 and that will be better. Oh, go assignments. Max X. Oh. These are called T max X and T max max. And T max max. There we go. Still, let's see. Here we are. We got some output. So this is just a part of our figure. And you can see that I got 80 lines printed and I only have 10 columns. So the mathematical coordinates are fine, but the terminal coordinates are not. So I did something wrong with the terminal coordinates. Yes, I switched those to. Ta-da! That looks okay. I like this. And can make it bigger. So let's make this 150, 40. Yeah, I actually don't have 40 columns. So there is something going on here, which is not too bad. The aspect ratio is not great. This is supposed to be a circle. This has to do with the fact that the characters I am using are not square. So in order to make this better, ideally I would use a scaling factor for the X coordinate to make it more, for the Y coordinate to make it larger. So you can try 1.5. This is just like a little parameter. Ideally, we should make all this configurable, and we're going to get there in a second. So here I have, in any case, the first step of the plan is done. So this compute function here draws directly on the screen, and that is not great. However, I also think that it's better if we don't change this code too much to become something else. There is something generally valuable with complex formula code, is that the expert that is writing the code originally, so supposing, just hypothetically, that this program here was written by 2 or more people, and then there would be one person who is expert at doing the domain modeling with the formulas and some other person who is better at doing the presentation programming. The last thing you want is to have the person who is doing the presentation programming take over the code of the modeling person and change it entirely to become something else. There would be 2 problems with that approach. One would be that maybe the person that will transform the code will introduce mistakes, and so the code ends up doing something different, and the modeling person will not understand where that mistake is. The other thing that might be a problem is that later, after this code has been deployed and has been maybe released, and there will be requests to change it, or maybe to change the domain model. If the main version that is visible to users is the version that's been translated, the person who did the domain modeling will not be able to modify it anymore. And so it would be necessary to pay the person to do this translation again multiple times. Every time there would be a change in the domain model. So all this is pointing us to this general idea that model-specific code, and that is this formula code in this program here, should remain as close as possible to the version that was implemented by the domain expert. And if we want to integrate this code in a larger function, this needs to be integrated without changes or with minimal changes. And so what we're going to try to strive for here is to inject a display function into this program without expanding those loops inside the framework that we are going to try to use eventually. To do this, we're going to do 2 things. And that is, first, we're going to make the parameters externally configurable. And the other one is to abstract the drawing code. So the parameters we're talking about are those here. And there is a ratio that we did not talk about that is going to control how circle like our shape is. This was a feature of the Verge version. So let's see how to integrate this ratio. Oh, the zoom factor. Yeah, so there is a zoom factor to be integrated, and that is to change the view pane based on the ratio. So we are going to change from x min, x max to and y min, y max to a center and ratio formula. So and then ratio, and then our compute function is going to be a function on the set of parameters. How does this computation work again? I need to do the view weight and ratio weight. Who? What is a view? Oh, I see. So it's like the reduction factor from the screen coordinates to the mathematical coordinates. And then we do the reduction. All right. So the starting point is going to be T max and like this. And then I will need to have a view weight. Yes. So let me remind me of this formula. So the the mathematical center is going to be the viewport width divided by 2 from the center. Yeah, okay, that's clear. X min. That is going to be from the center and the x width divided by 2. Same for and the x width, it says width of the display times the ratio. And then the loop is going from the terminal and instead of y max, y min, I have y width and x width. Why is this complaining? What am I missing? So this doesn't need to exist anymore. Oh yeah. So what we did here, we kept the main code below, but we transformed the coordinate system. Instead of having a bounding box in the mathematical plane, we have now a center and ratio parameters. And so we are going to do this. The center is going to be 0. And the ratios. I don't know yet what I want, but we can maybe copy the values from the other program, something that goes in that area. So this value 45, that brings me that squeezes the figure so that is small, a tenth of the screen. And the one here is going to be 0.1, and the rate difference between ratio for x and ratio for y is accounting for the fact that, say, I am using a font that is about twice as high as it is wide. So let's try this program. And I made my figure round and it fits on my screen. Cool. All right. So what we achieved here is to lift the parameter space into this struct so that the mathematical parameters are not anymore constants at the start of the function. Now I have here parameters coming from the screen, and I also want to make those parameters that I don't need to write explicitly, but they're not going to be part of the mathematical parameters. They're my domain parameters, if you will. But they're going to come from my display, and so my display is going to be an abstraction. And so it interface, I can type. It's going to have a size. This is a dummy struct that will implement this interface for the purpose of testing, and later on we're going to implement the interface with our framework. This has extracted the size definition away from our function so that later on we can change this size somewhere else without ever having to change the implementation of this function. So we can check, it still works. What we're doing bit by bit here is to change this program to comply to what we want to our plan. And every time we keep it in a runnable shape. So here I lifted the size into an interface and immediately created a dumb implementation of that interface for the purpose of testing so that the program I was working on is still runnable at that moment. This is generally a method that I like to use. It's very close to what is called test-driven development. It prevents having multiple hours of extents of time where, say, there is uncertainty about whether the program works or not. With this gradual method and approach, at every moment I can go and run the program and verify that it actually works as intended. So I have here this display that is not yet configurable, but we'll see that later. Another thing that is fixed here today is the program prints out by calling this print function, and I actually don't want to have that either there. I want the computation to delegate the task of displaying to our external display. So I'm going to lift this by saying disp dot draw at the coordinates tx, ty, and I. I is the color I need to draw. And this value of I is going to be between 0 and max I, but the display code does not know this. So what I really need is to have some notion of a range, a color range. And that is going to be given to me by, say, display ahead of time. And because I might still need to do something special at the end of every line, I'm going to add another API for this. So now I can remove the display specific code from my main computation loop. It hasn't changed significantly since I wrote it the first time. And now I can define an interface in this here. And so I will have draw cell and then value and then finish line and then color range. And my fake display is going to implement those things using the code I had earlier. You're noticing that I wrote the value parameter here as a separate positional argument, even though it has the same type as x and y. This is because it's possible that we will discover later that, I mean, it's likely, I'm speaking from experience, that the type of the value is going to be different from the type of coordinates. And so for things that I keep them separate so that the modification of the code will be easier. So my boxes are going to be here for clarity, sends a value like this. All right. And then we need some documentation here. Going to be inclusive, exclusive. Does it still work? I believe it does. So now we have a display interface with a dummy implementation. We have a domain-specific parameter struct and our compute function that has barely changed since we first started implementing. So this function is going to remain there. We don't need to change it anymore. We have completed our core computation core conversion to an abstract version. And now we are going to display this on the screen using the new framework. actually call that a to-this. And then when we are done with this first integration, we're going to integrate a keyboard to change our parameters. Now, this is where the complexity starts, because I've never used this, this TView package. This is its documentation, and there must be some kind of examples that we're going to run. Box is tview.newBox set border. I don't want to have borders. Do I not want to have borders? Let's keep borders. tview new application set root run. We're going to have an exit function. Okay. Yeah. All right. So this framework has given us a box. It doesn't do anything. That's because we did not connect our computation function to it. What I understand is to do without reading the documentation is that the box is an abstract object that is an in-memory data structure where our program can draw contents. I don't know how yet, but we're going to figure that out. And then the application concept is the other data structures that represent the runtime, event loop, and other event handling. Why I know this without reading the documentation is because a lot of interaction frameworks have those two different concepts and those abstractions, and they are extremely common. They recur very often, and so after seeing a couple that have the same principles, it's really easy to get to this intuition without having to dive into the documentation. So what it's doing here, create a new application. It attaches the application to this box, meaning that when the application runs, it has to display that box. The second argument, true, as the documentation says, is to make it full screen. And then once the box is displayed, then the run function will run the event loop. And because we did not attach any event handlers, it is just displaying the box without doing anything. So what we want to do is to attach our computation function to, say, to the display. Even without interaction with keys, we still want to call our compute function. How do we do this? There must be a place in this API where we can attach a draw function to a box. So this is a box, and I can say set draw function. So that's get draw, so I must have a set draw func. The set draw function takes a handler function that takes a screen abstraction, coordinates, width and height parameters, and then returns some values. And what does it do? It returns the box's inner dimensions. Oh, okay. So that means I can use this draw func to maybe create a widget on top of it. It's okay. Let's try this. So I need a function that has this abstraction here. All right. So we have a TCL.screen. I don't know what that is, but I kind of suspect this is an interface that gives me access to a way to draw to the screen. So we're going to check that. Can I go to definition with this? Doesn't seem like it. Let's peruse the documentation. The screen abstraction is an interface, and it has a set cell. Oh, it's an older API. Okay, set content. Set the content of the given cell location. If the coordinates are out of range, then the operation is ignored. The first rune is a primary non-zero width rune. I like this. Rune is what I used in my display code already. Like these strings with special Unicode characters are actually runes, so I can display those runes at the coordinates. And then there will be a style, which likely we're not going to use because we are using those boxes instead of colors, but we could introduce colors later on. We'll see. And then we have a style default. Style default is great. All right, so default style here, no combination characters, and we have a rune. So here we have what is called an impedance mismatch to solve. We have created a display interface with those four methods, and that is what our code here wants to use. And the TView framework gives us a tcl.screen that provides different kind of methods. It also gives us the coordinates as variables and not as methods on the interface. So I need to translate those things here into our display interface. I have chosen to do this because generally that is a problem that is always regularly the same. Once the domain-specific code has been adapted to be integrated in a larger framework, it's extremely rare that folk go back to it to modify it, or that they even want to do this. Maybe they lose the expertise to do so. Maybe they are very risk-averse and they don't want to tweak it anymore. And therefore, this display interface that we've defined is somewhat tightly bound to the implementation of the domain-specific code. That means that we're not going to be keen to want to modify this. So instead of injecting the abstraction from the TView framework into our computation code below, we're going to keep the display interface and we're going to create an adapter between the two. The adapter is going to be a struct and is going to implement the display interface. So I make an interface implementation assertion like this. And that struct will have our methods that we have from the interface here. And it's going to delegate their behavior to the TView things. Oh, come on. There we go. And here I need to make them methods. So what is the size of my display? Well, the size is given here. So I will make a copy of the size here. Then what is the color range of my display? Well, we are going to keep the notion of boxes in this adapter, except that we're not using any more strings, but we're going to use runes. And that means that we're not using the double quote, but the single quotes. And the size, sorry, the color range implementation is going to be the same, except we are going to use our runes. Right? What do we do for finish line? In this framework, we don't need to do anything because the T-view and T-cell abstractions don't do anything special at the end of a line. And then what do we do for draw cell? Then we extract a rune from our value. And then we say a.screen. What was the name? Set contents. And then our rune. And what is screen? Is a T cell dot screen. All right, this has a this implements the methods by reference, and I'm passing them by value, and it's because it wants to point to a reference. So let's allocate this adapter at the top. I'm making an assumption that the code is not concurrent, and therefore it is safe for me to allocate this on the stack. Sorry, on the heap and share it. That will be fine. There we go. And that has achieved our adapter. So we take the parameters coming from TView, we put them into our own struct, and then we compute with that because our adapter implements our own interface. Then it makes a complaint to us that set content is missing parameters. That is true. What? Style. Style? Why is it not happy? I heard style default. Style default. There we go. Let's see what this thinks. We have achieved success. This thing has agreed to draw our shape within the framework, except that what we see here is that the box frame that we had originally when we made the first implementation with set border, set title has not really agreed with us. Our program erased it, and that's because we need to shift our computation by 1. And now we have a box. Cool. All right. All right. Now our program is able to draw that box on the screen, but it's not super interactive. I don't even know if it is able to react to size changes. Oh, actually it is. All right, so that is a good surprise. So our program is automatically informed by the TView framework when the window size changes, like the font size changes. It will recall the draw function with a new width and new height corresponding to the new font size on the screen. And that's why our picture is automatically scaled. Now, what we want to do is to change the parameters based on key presses on the keyboards. How are we going to achieve this? There must be somewhere in that framework a way to register event handlers. And we don't know how to do this yet, but we are going to do that now. So I see here an input handler, set input capture. I don't want a mouse. There is a wrap input handler. Interesting. I don't know how this works yet. Application maybe. Set input capture. I don't want this. Enable mouse. All this mouse stuff is fun, but it's not what we want. We want to do with keyboards. All right. I have no idea. I have no idea. So in this way, we need to go at the tutorials or maybe the wiki and get some examples. A passwords manager. Let's see. Our to-list. Let's see what those programs do. There we go. App set input capture. And then we give it a function, and there is a switch that will do things, and we can return the event to say whether we process it or not. So here we are, app.setInputCapture. This is what we need. Is this up to date? Not enough elements. TCL event key. I like this. And what we did say earlier is that we wanted to have zoom in and zoom out with the page down and page up keys. So I'm hoping that this key has page up and page down. Yeah, it has. P dot What is it telling me? Oops, come on. Oh, there we go. It worked. Except that it only recognizes page up to zoom out. Let's do the zoom in. Page up, page down. Sweet. Sweet. Then we're going to recognize the key left. So what we want for key left, we want this to move the center by a factor of our ratio. I don't exactly know how much of it, maybe divide by 3. What did I choose in the other program? Oh, by 10, I suppose. Okay. Then we can do the same with, say, key up and key down. It's going to be key down, I think. Key up. I don't remember in which direction the screen moves. And then everything that's X is going to become Y. Come on. Okay, I actually get confused. It was the other side. Better. Absolutely better. This is sweet. We can navigate. Now, we got ourselves a program that works with black and white and is pretty nifty. What if we wanted to use this feature specific to this framework that is with colors? Maybe we can spice it up with some colors. So what kind of behavior do I want with colors? I still want the boxes, I think. And then I probably also want to give them color. Or maybe I don't want the boxes, I just want colors. We can experiment a little bit. But I also especially want to understand how colors work. So how do colors work? We heard already about this style. And there is a way for this to do style. So style represents a complete text style and encoded as a 64-bit integer. But it tells me it's a struct, not an int. How can I create a style from other things? Style, new style. Do I have a new style? Style. Oh, returns a new style based on S with a background color set as requested. I see. Okay. So we're going to change the background color. And colors are integers. So we're going to play with blues for the time being. And we need a color is RGB. Cool. Cool. And that means that if we have a 24-bit RGB value, we are going to have values for blues that are going to be between 0 and 255. And that means that we can change our formula here. Our adapter is not going to be style default anymore. So we're going to have a blue between 0 and 255 inclusive. So that is going to be value times 255 value. How does this work against 256, I suppose? How do I get everything inclusive? So the maximum value is going to be 255, yeah. Oh, value is 255 already. Oh, all right. Then we're going to convert this to RGB. So that's going to be simply uint64 of blue because it's the lowest byte in the value. And then I'm going to have a style. It's going to be tcell.color is RGB. And then this, and then this, and then oops. And then let's take one of these, or just a space. And then our color range is going to be 55. Oh, 56. 56 is it. And background. Okay, this is a color, and then the style is tcell.style default.background of C. Thank you. Are declared not used, because I'm not using this rune thing anymore. Did not work super well. What went wrong? What went wrong? That is because I don't have enough iterations, I believe. We're going to start from the end. Did not work. My terminal has colors, and yet it doesn't work. It's possible that the terminal actually doesn't really understand 24-bit color. This is kind of an advanced feature. So we're not going to do too much color with 254. We are going to do the lower color scheme. So it's going to be 16. So simple color. And then this, and then the maximum value is 16. Still no dice. I have no idea why this is the case. Maybe it's because it doesn't like when I'm printing just spaces. Yeah, so spaces don't really look like they have color. Color is not convincing. So this background thing here is not helping. So let's try with a foreground color. Still no dice. The value is between X and Y, between 0 and 16. Foreground doesn't work. This is odd. This is very, very odd. How does these colors work? We're going to explore this framework. The path to it, more tcell color.go. So color valid. Oh. Yeah. Better. Okay. Okay. Now we're back to business. Background, space. Yes. Look at this beauty. And now we are going to go back to our 24 color scheme. So blue, RGB, and then tcell dot color. What was it? Color is RGB. Better. I like this. The reason why it's very dark is because we are starting from, we have a maximum of 100 as a value, and well, and my terminal only has probably to have 56 colors and not 16 million. So what we're going to do about this we're not going to exploit the entire range of 256 values. We're going to have only a range of, say, 16, 15 values. And then we're going to do 255 minus value times 15 times 16. And that will spread them across the color range. And now we have blues, sorry. So progress is made. And then the question is, are we happy with just blues, or do we want more colors? Well, I would say at this point it looks like more an academic exercise. What if we wanted to make this configurable with the color palette? Let's make a configurable color palette. Okay, so that is done. And so we're going to have a bonus exercise. Switch between color palettes. And it's been a little while since we started, at least 1 hour. I need to make a cup of tea, and so we will reconvene in a few minutes. So enjoy your break. Don't forget to hydrate and stretch, and we'll be back within maybe 5 minutes from now. See you. And we are back. Our program is able to print this, and we want to make those colors, well, probably more pretty and also configurable. And so there will be multiple improvements, but we want probably to switch between palettes. I'm going to remove this computation first. This way we have a more natural palette. Oh yeah, I also remember this needs to go to 1000 this way. We will have more details in our color. But all this is very blue. And we'll see. We'll see in a second what we do about this. Palettes. So what is a palette? A palette is a function. Well, it's a data structure with a function that gives us a color, an RGB color of 3 values. So we're going to do palette and we're going to change our, so this is a value color range. This was with modulo. Modulo. I suppose this can continue to exist. I'm going to say a palette is something that takes a value between 0 and max. And gives us 3 values. And we're going to have our blue values. So max val. We'll see. Blues. And the blue, we take our computation from what we had earlier. Where was it? Where did we have our blues? It's going to be our max value. So max value is going to be 255 times float of value divided by float of max val. So I'm scaling the range of 0 to max val to a value between 0 and 255. And the result is an integer. Now I have this palette here, and I want to inject it into this here. So going to be RGB. So what is my current palette? We'll see. And so it's going to be an integer. And then our color range is going to be a dot color scheme. And now how do we make this? Is going to be R shifted by 16, then green shifted by 8, then blue. and the rest doesn't change. And our current palette. So this rune thing corresponds to our dummy display. And this dummy display we're not using anymore because our test program has evolved beyond it. So I'm going to take this and go to a dummy display.go file here. And, oops. And our main program test doesn't have it anymore. And then we have color scale. So color scale adapts 100. And the current palette is not specified at this point. That's okay. It needs to be in the adapter. Where is the adapter? Adapter. And then we have our display. It's here with a.current palette. There we go. Still works. My display is still being used somewhere. Oh yeah, this code is dead. We don't need it anymore. Runtime error. I like this. So we made a mistake. 190, 154. Drew cell. C range. So C range is 0. Color range. Oh yeah, we did not initialize the color scale properly. Did we not? Oh, yeah. We are overriding the field here. So we need to not override them. Come on. Better. All right. So there is a little of a strange effect here, and that is probably because our eye is more sensitive to the brighter shades. We'll see. So this blue palette is very dark, and I don't mind this. So values that is at 0. Oh yeah, the more common values. That's what it is. The more common values in our figure are close to 0. So we're going to start from we're going to start so what we're going to scale our value by 2. And then we are going to offset it by 0.5. So our value scaled is going to be between 0 and 1 exclusive. That makes it go between 0 and 0.5 exclusive. And that makes it go between 0.5 and 1 exclusive. So our color is going to be between 128 and 255 exclusive. Now our colors are brighter. I really don't think this is really better. I don't actually like it too much. But the beauty of it is that we can now make multiple values, multiple palettes like this. So we are going to have our bright blues, and then we have our dark blues. And this is the original one. And we are now going to try to switch between them. So what we really want is to switch the current palette here. So case tcell dot space. I suppose that is a key. Is it? Yeah, it's dark blues, bright blues. Bright blues does not implement bright blues, dark blues, and then tcl.space, key space. Key SP, maybe? What keys are defined? I actually don't remember. Did I see that somewhere? Key, space. Oh, maybe the space is expressed as the ASCII code. Let's try this. And that is going to be a.current palette What is happening here is that we are creating a cyclical navigation with a space key between all the palettes. So there will be an integer variable called current palette index, and then every time we press space, it will go to the next one, and we preserve the current one in this variable. So these two variables, the index and the all palettes, don't exist yet, but we are going to do this here. This did not seem to work. It doesn't look like the space key is represented with space character. And that is strange. I actually don't know how a regular key is handled on this system. So that's another thing we need to learn. How do event keys work? Type event. No, that's a TCL. We need a TCL event. Key. Event key. For normal keys like ASCII letters, we use key rune, and then the rune member. There we go. And so if event.rune, then we do the thing. It looks like we have success. We can switch between the palettes this way. That is nice. Of course, our palette here doesn't really look great, and I really wish I had a good formula, but this is okay. We can explore this. So what we want to do is not go on the formula with RGB with just one of the colors. We want to have a hue saturation value formula, because a hue HSV value is extremely pleasant to work with, because the hue decides the color on this gradient here on the screen, and then the value decides how bright it is, And then the saturation is how white it looks or how gray. And so what we are going to do is take the maximum saturation, then the maximum value, and then switch the U. Maximum saturation, maximum value, and change the U between the range of values that is available. So what I want is a formula to do this, because the values for the U are whatever it is, and I want that to be my source code. So I want a formula. Thank you. Oh my. So the U is an angle between 0 and 360. I'll take that. And then there is this mapping with the value of x. That is whatever it is. This is not meant for use by a computer, because I probably have an angle in radians as opposed to 2 degrees. Well, I'm willing to play with this. I'm okay with that. And then the 60 degrees here. Yeah, it's okay. We can work with that. So saturation is going to be 1, so that's going to be simplified. And then the value is going to be 1. It's going to be simplified, so C is always 1. So that's always 1. And it's going to be minus 1 here. Oh, V minus C. Okay, so V is 1, C is 1, so small m is going to be 0. So this offset here is going to be 0. So that simplifies. So I just need to compute this, these cases here. I'm okay with that. And H is CU. And C is this. Cool. Actually, it's not too complicated. Use so I have a U value between 0 and 1, and I want it to be between 0 and 360. Okay. And then I want to compute this. So C is going to be what? C is the value times the S. So value is 1, saturation is 1. So it's going to be C 1. Okay. Oh, C is always 1. Okay. I like this. And then X, C times 1 minus that is interesting. Mod 2. What is mod 2 supposed to mean? That's the remainder of the divider by 2. So it's a value in degrees. What is this? So hypothetically, suppose I have a value of U that is 0. So 0 divided by 60 degrees is 0. 0 mod 2 is 0 minus 1 is minus 1. So 1 minus minus 1 is 2. So I'm going to have x that's going to be 1 minus plus 1. So it's 1 plus 1, 2. So C times 2. So x is going to be 2. But that's odd because x is supposed to go between 0 and 1. That is a problem. This formula might not be correct. So let's see. I have JavaScript disabled on this browser, haven't I? Yeah, let's enable it again. So U is 0. Saturation is 100%. What does it tell me? 250. RGB. What did C code for? H is 0 divided by 60 is a 0, mode 2 minus 1. And the absolute value, I forgot. So that's what it is. So this is minus 1. So it turns to plus 1. So I get 1 minus 1 gets 0. So x is 0. Haha. Okay. I actually don't understand what this modulo 2 stands for. It's a remainder of the modulo. So it gives me something about a value between 0 and 2. Yeah, well, I'll take it. I'll take it. Math.abs of h, and that's scaled times 60 divided by 60 modulo 2 minus 1. 1 minus. Cool. And then m is v minus c. C is 1. V is 1. So m is 0. So I will actually ignore m. And then I have these cases here. So and then I have a switch. And then I have cases. So so I'm going to call it H. Come on. And H is class smaller than 60. Then RGB is CX0. Alexis. And then how many of these cases do I have? I have 6. And then the values are increased by 60 every time to 40, and then 300, and then 120, 80, 240, 300, and 360. And then the permutations, CX, XC, 0 CX, 0 XC, X0C, and C0X. Case, because I have a straight comma here. All right, and I have use. And I forgot to scale them back to, so I have integers and my r's are floats. And so these are 255. Off we go. I think this is fine, isn't it? Yeah, probably fine. C. And so we add our use here. Oh, operator modulo not defined on floats. Not defined on floats. So this is not great. So I have math. Probably, I hope I have a modulo operation on floats. Mod. Oh, look at this. Math.mod. Yeah. And those arguments here are floats, and I need to convert them back to integers. Cool. colors, very bright colors. Very pretty, very bright. And if I make my font smaller, it should increase the resolution of my picture. And I see my beautiful fractal with very pretty colors. Isn't this great? Just colors, pretty colors everywhere. And so the Go version is visibly slower than the Rust version I wrote before, but I think that it's okay. I still get a lot of my pixels on the screen. Oh, Bunker is on the chat. Nice idea to open a window of my day-to-day work. This is not only a window, this is actually a way to be disciplined and try to fix a project within a time frame. And that is something that I decided I want to become better at, and that is to start a task with an objective to finish it within a time frame. So thank you for the message, and I'm very glad that you dropped by. Cool. Anyway, so this is our achievement for today. I did not know how to get there when I started. So let's get back to a regular font size. I explained that I wanted to get to know this framework today. And my methodology was to implement in Go a computation that I tend to reuse to discover things in programming languages, which is the Mandelbrot set computation. And it was the first time actually I implemented that in Go, because I never did before. That gave us this little double loop, which we could possibly further optimize if we were performance constrained, but we're not. And then bit by bit, we extracted the logic to become configurable. Then we created a generic interface with some display code. Then we implemented a pseudo display with Unicode characters that gave us a shades of gray. And then bit by bit, we extracted this into using the TView framework. And we had to create a interface between the function parameters provided by TeamView and the display interface that our compute function was taking. And so we created this adapter for this purpose. And then initially our adapter was only using the same shades of gray Unicode boxes to create a shade of gray display. And then after that worked, we added some handling of input keys for changing the zoom factor and navigating the image. And then after that, we said, well, TView is telling us that we can do something with colors. And so I experimented with some formulas that were not exactly successful. These are too bright, too dark. I wasn't exactly sure what to make. But eventually we decided, well, we're going to experiment with palettes. We might as well make the palette configurable. And so we have now a shifting between palettes thanks to the space key. And as a closing step, we created that use palette that is using an HSV, so hue saturation value to RGB computation, to keep the value and the saturation parameters to the maximum and only change with the hue, which is a color, the visual perception of color. And that gives us a lot of very fancy and pretty bright colors. And that's what we see here. So what I learned today is that TView is extremely close to a lot of other interface toolkits that I have learned in the past. It has abstractions for the canvases or the items that are on the application side, like the abstract objects that the application can manipulate. And then it has an abstraction for the main run loop that has the parameters for what is going to happen on the terminal. And it is also event handling with callback based for every key pressed. And because Go gives us closures, we can modify the variable in the main program here from the closure without having to pass hidden parameters through those closures. So cool. At least TView gives me a canvas to draw on. I did not really learn here a framework to make user interfaces with user inputs and things on the screen and so on, but that's not exactly what I was looking for anyway. I think that having a canvas to make pictures on is much more interesting than forms where people can enter text or choose values from a menu. But it's okay. It's okay. I feel happy with this result. So here we are. I think for today it's going to be good as is. It's been nearly 2 hours anyway. I will take comments as usual. Banker, funny thing, I wrote my first canvas-based render for Mandelbrot set in JavaScript last Friday. Were you inspired by Google's last Friday doodle? I was not. In fact, I rarely use Google. I use DuckDuckGo, so I wouldn't know what the current Google Doodle is. As I explained initially, I use the Mandelbrot set computation as a go-to idea algorithm for exercising new frameworks or languages. And today I had an intention to learn about this TView framework in Go. And so I thought, well, in terms of making an interesting program, I'm not going to make a form in TView. I might as well make something on a canvas. And so what could I draw? And the only thing I know how to draw that is pretty is a Mandelbrot set. And so that's where I got there. But I'm going to check out your link and Twitter because I'm curious about what you were able to achieve in JavaScript. I actually think that JavaScript is cheating a little bit, given that the entire browser is there to help you with drawing stuff on the screen. But I'll take it. If I were to do graphical interfaces these days, I wouldn't do anything else than JavaScript anyway, because I want my applications to work anywhere, and that's what a web browser is for these days. So cool. Glad to have some colors on the screen today. And next time, I wonder where it's going to be. Next time is going to be next Monday. I might still be on vacation. Isn't sure yet. We'll see. But if I'm not, we are probably going to do something web server related. So we'll see. Thank you a lot for being there. And I hope to see you again very, very soon. Have a great day.